Greetings, it's Paul with the introductory video for Class 22 of Math 117. I am going to derive the Black-Scholes option pricing formula for you. This derivation is simpler than either of the ones in Deneen. I have eliminated the complication of a non-zero interest rate. I can reintroduce it at the last minute, and I've also decided I'm going to base this on the martingale properties of the Wiener process, which you've proved. So let me remind you about the Wiener process, which is basically a sort of continuous limit of a random walk with steps of plus or minus 1, each with equal probability. This, as you recall, is a martingale whose expectation is 0. Curiously, its square minus t is also a martingale with expectation 0. That means that the variance is equal to t, and the expectation and variance fit together in the nicest possible way. W sub t, this random variable indexed by time, has a normal distribution with expectation 0 and variance equal to the time interval t. If you consider 2 times s and t, where s is the earlier time, the difference between the values of w at t and s has a normal distribution whose variance is just t minus s, and there's a nice independence property. If t and s are both greater than r, what happens in the interval between s and t is independent of what happened up through time r. Best of all, the exponential of some quantity sigma, the volatility, times w sub t minus sigma squared over 2 times t is also a martingale, and that's going to be the martingale that describes the evolution of stock prices with time. As I said, I'm ignoring the issue of interest. So we have a very simple model with no mention of mu or r in it. The random variable x sub t that gives the value of the share at time t is the value x sub 0 multiplied by the exponential of a deterministic part minus sigma squared over 2 times t plus sigma times w sub t. That first term, you'll recall, has to be there because otherwise the random walk in the exponent has the effect of making the price gradually drift upwards. You can find the same formula in Deneen, but he distinguishes between w sub t and w sub t tilde by setting the interest rate to 0 and setting mu equal to 0. I've made those two things both the same. In class, I will show you a very nice little R script that I've written where I will generate graphs showing the evolution of share prices in accordance with this model and do a little bit of simulation from it. Now let's get busy with the Black-Scholes formula. The share price evolves in accordance with the risk-neutral probability measure that comes from the Wiener process, and therefore to find the value of a call option at time t equals 0, all I have to do is look at the maturity date, say the value on the maturity date is x sub t minus k. I take the exponential of that, the expectation of that quantity, in accordance with this risk-neutral probability measure given by the Wiener process, but I'm very careful to set the random variable equal to 0 if the share price is less than the strike price. W sub t has a variance equal to t. I'd really prefer to deal with a standard normal distribution where the variance is equal to 1, and I'll do that by just writing w sub t as y times the square root of t. That means that y will have a variance that's smaller by a factor of t than wt, just the one that we want. And now we have the quantity we need to evaluate. I take initial price x sub 0 multiplied by this exponential that gives the time evolution, subtract off the strike price. I want to calculate the expectation of that, but only when the random variable has a positive value. How do I do that? I multiply by the density function for the random variable y and integrate. But there's a tricky part here. I only want to do the calculation when the option is in the money. So I have to figure out for what value of the standard normal random variable the price on the maturity date is equal to the strike price. This is elementary algebra. I set the evolved share price, which is here, equal to the strike price. I insist that that be greater than or equal to 0. In other words, the share price has to be greater than or equal to the strike price. I take the logarithm of both sides to isolate the exponent, isolate sigma square root of t times y on the left-hand side, and finally divide through by sigma square root of t to get an inequality that is satisfied whenever the option is in the money. Following Deneen, I'm going to call that quantity t sub 1. And now I've got my answer. This, by the way, is what I was unable to do in the R script. I did a numerical approximation to this integral, but because R doesn't do symbolic algebra, I couldn't get a closed form expression for it. So there's the value of the option. It gets multiplied by the density function for the standard normally distributed random variable. I integrate from t1 to infinity, and there's the answer. Let's see if we can simplify this. First thing I'm going to do is split it into two terms. The first term involving the share price, the second term involving the strike price. That's straightforward. And I remind you what T1 is equal to. But I'd like to put an interpretation on the two terms. The first term says calculate the expectation of the evolved share price, but only over values for which the option is in the money. That would actually be the value of a contract that gave you one share of the stock, but only if the value of the stock you got exceeded a specified strike price. The second term is almost a calculation of the strike price. If I integrated from minus infinity to infinity, this integral would just equal k. So you can think of this as k multiplied by the probability that the option is in the money. Now let me introduce a bit of terminology. I need a name for the function that specifies when a normally distributed random variable with expectation 0 and variance 1 has a value less than some real number, little x. Deneen calls this function capital N of x, and so will I. It's the integral of the density function from minus infinity up to x. Usually we will be integrating from some value up to plus infinity. So for this function, which incidentally is available in R under the name p norm of x, if I take 1 minus this, then I am doing the integral from x to plus infinity. But because the density function is an even function, integrating from x to infinity is exactly the same as integrating from minus infinity to minus x, and I have shown that 1 minus n of x is equal to n of minus x. This will be useful on a couple of occasions very soon. Now let's evaluate the integrals. The harder one is the first one. And if I stare at this for a while, I say, hey, this exponent is a perfect square. If I expand this, I'll get an e to the minus x squared over 2. I will get an e to the minus sigma squared over 2 times t, and I will get an appropriate cross term. So I just make the change of variable y is equal to x minus sigma times the square root of t, and now I have something that is the integral that defines the function capital N, with the argument being sigma times the square root of t minus t1. Hey, did I change the sign there? Yes, I changed the sign. I exploited the fact that, as I just proved, 1 minus n of t is equal to n of minus t. Here's what t1 is equal to. When I subtract it from sigma of t, something very nice happens. The sigma of t is, of course, sigma squared times t over sigma of t. So the effect of this subtraction is simply to change the sign on this term. The second integral was absolutely straightforward. It was just k times n evaluated for the argument minus t1. We put these together and we have the famous Black-Scholes formula in the special case where the interest rate is equal to 0. How are we going to put the interest rate back in? Well, there's the formula we just derived. If we have a non-zero interest rate, what do? We discount all future values back to time t equals 0. And once we've done that, everything is exactly the same as when r equals 0. You can say if we only express values in terms of time t equals 0, we're effectively dealing with a change situation in which there is no interest to be taken into account. What's the only thing that has to be changed? Well, we've got to discount the strike price, which is a value at time capital T. We have to discount that to k times e to the minus r capital T. So 3 places I will introduce the factor of e to the minus rt. Usually what's done here, though, is to say the log of 1 over e to the minus rt is, of course, just r times t. So we put the r times t there and the r times t there. There is the version of the Black-Scholes formula that won the Nobel Prize. After about 10 minutes of effort, I managed to get it successfully typed into an R script, and when you need to evaluate this, just fire up R and use blackscholes.r. There are also online calculators that will do this for you if you like. Well, we've done it. We've derived the Black-Scholes formula, and remarkably, I'm done in less than 15 minutes for once.